All right, well, in this lesson, 6.2, we're going to use the exponent rules that we're already familiar with to simplify these expressions that have rational exponents. And so we're going to have to remember our rules for exponents as well as remembering how we deal with fractions. So in number one, we have the same base. So we have two exponential expressions. We just have to happen to have exponents that are fractions instead of just whole numbers. And so but the bases are the same, which is what we always look for when we want to multiply fractions together. So the rule states that when we are multiplying two exponential expressions together, they have the same base. We rewrite the base and we add the exponents. So we're just going to take that 1/3, we're going to add to it the 4/3, and that will give us an exponent of 5/3. Remember, we're going to try to write the exponents, the fractional exponents, with like in a little bit more of a horizontal view as opposed to that vertical view, so that it doesn't end up looking like 7 and 5/3, like you're trying to make a mixed number. On number two, we have two exponential expressions, both with the same base. This time we want to divide them, so we're going to follow those rules, which just say to rewrite the base and then subtract those exponents. So we're going to take 2/3, we're going to subtract it from 1/3, and that will give us 1/3. So our exponent then is 1/3. So we end up with 4 and 1/3. On number three, here's where we have one exponential expression. So you only have 6 to the 2/3 power is your exponential expression. We only have one base, and we're taking that exponential expression and we're raising it to a power. So this is a power raised to a power. And this is the rule where we rewrite the base of 6, and now because we have a power taken to a power, we're going to multiply those two together. So of course you have to remember that when you multiply fractions together, you're multiplying the numerators and multiplying the denominators, and then we're going to reduce, just like we would if we, except let's make sure we reduce correctly, just like you would in any multiplication problem with fractions. So instead of writing 6/12 as our exponent, we're going to write 1/2. So now in 5 and 6, we're going to move to radical notation. So we've got to remember the rules for radicals. If you have two radicals that have the same index, so again, the index means this number that's just sitting in the little v of the radicand sign. So if those two match, then you can multiply what's inside of the radical, which we call that the radicand. So I'm going to rewrite the fourth root symbol, and then I'm going to multiply 2 and 8 together to give me 16. And now here I can actually reduce that. The directions asked us to simplify it, and I can simplify the fourth root of 16 because the fourth root of 16 would be 2. All right, 2 to the fourth power gives me 16, and so the fourth root of 16 is 2 itself. On number 6, we have the same idea. We have two radical notation, and they both have the same index of 4. So because of that, we can divide what's inside of them. So if we rewrote that, it would look like the fourth root of 192 over 6. Okay, so if we divide 192 by 6, we're going to get 32. So we're talking about the fourth root of 32. Again, I'm getting the 32 just by doing that division there. 32 there is not a perfect fourth root of 32. So they're not, what I mean by that is 16 is a perfect fourth root because it has 4 2's multiplied together to give us 16. We don't have a number like that for 32. So what we have to do is prime factor the 32. So that is where we use that factor tree. Okay, so there are our prime factors, but now instead of we're not looking for a square root anymore. We're not looking for two factors that are the same that multiply together to give the number under the radical symbol. We're looking for 4 now because we're talking about a fourth root. So every time I see 4 of a number, 1, 2, 3, 4, 4 of the same number, I can pull that out from under the radical one time. So I've got 4 2's. I'm going to pull that out. Whatever's left, which is this extra 2 right here, I have to rewrite that fourth root radical symbol and leave the 2 under there. So this is the same principle that we did when we were simplifying square roots using prime factorization, but now you have to pay attention to what the index is sitting inside that little v of the radical symbol. Okay, it's no different. It's just that you've got to pay a little bit more attention to what they're actually asking you. On number 10, we have a fraction raised to the third power. So we each of the numerator and the denominator is going to be raised to that third power. So I'm going to say if I want to turn it into a radical expression, then I'm going to put the cube in the v. We're looking for the cubed root of 54. All right, and we could technically put that in parentheses and put the 1 on the outside, but if we're raising something into the first power, it's just the same, so we don't have to do that. And then that denominator also gets raised to that third power, and so I'm just going to go, I'm not showing it 54 to the third and 64 to the third, but I'm just going to go ahead and stick both of them into radical notation. So maybe I should show where I'm going. Like technically the first step would look like this. Okay, or you could raise the entire thing, to the 1/3, but this is probably the easiest way to do it from here. So technically, this would be the first step. We're raising the numerator to the exponent as well as the denominator, but then in order to simplify this, we have to go to radical notation. It's really the only way to do this problem. So we're looking for cubed root of 54, and we're also looking for the cubed root of 64. The cubed root of 54, there's not a perfect cubed root of 54. And so we have to go off to the side and do our factor tree. Remember, on the factor tree, you're done with the branch if you have a prime number. So all of these are prime. That's why we call it prime factoring. You take it down until all the numbers left are prime. So now I'm looking at the index. I need 3. Because I'm looking for a cubed root, so I have 3 3's here, so I know that I can pull that out one time, and I have a 2 left over, and that 2 has to stay inside the cubed root radical. So the 3 times the cubed root of 2 is the simplification for the numerator. We have to do the same thing with the denominator. So we're going to prime factor the denominator. I'm going to come out here to the side to do that. Okay, again, I'm looking for pairs of 3. So I've got 2 and 3 here. Okay, so I'm going to be able to pull out 1, 2. And then I've got another pair of 3's here, so I'm going to be able to pull out another 2. All right, so actually this one was 64 is a perfect cube. I made a mistake when I said it wasn't. And so you could have just pulled straight out that 4. You need to multiply the 2 and the 2 together. So the final answer would be this right here. So you can see, even if you make a mistake and you think something is not a perfect cube, like I did on the 64, it's still going to work out in the end. You'll just end up with a whole number, 2 whole numbers or more maybe even that have to be pulled out and multiplied together. All right, on 13, they ask us to simplify the expression. And now, if you'll notice, the difference here in this set of directions is that the base is now an exponent. So in 13, we have to check to make sure the variables are both the same for our bases, and they are. We have an x as each base. So we're just going to rewrite the base. We're going to add those exponents. And again, we're going to simplify if we can, which we can simplify 9/3 to 3. So this is just x cubed. The same rules apply. You just have to account for making sure that the variable is the same on bases that you're combining. For number 14, we have a little bit of an unusual situation here because you've got x raised to the 2/5 power, but that whole expression, that exponential expression itself, is under a square root radical. So just take it step by step. The rules state that you write out what's under the radical symbol, and you're going to take that, put it in parentheses here, and we're going to raise that to the 1/2 power, because the reason for that 1/2 is there's really, a 2 sitting in here. Since this is square root, we just don't write it, and the whole thing is to the first power. We don't write the first power because we don't, if we're only raising something to 1, we don't write that out. It's just assumed. So you take what's under the radical. The rules are the same as we have done previously. It's just the strange thing about this one is you have a variable raised to a fraction exponent. All right, so, but this is not simplified. Again, they asked us to simplify it, and we would never leave a power raised to a power and say that it's simplified. So again, there's one base. Okay, this is like number 3 up at the top where we had one base of 6. Here we have one base of x, but we have a power of 2/5 raised to another power of 1/2. So this is where we multiply those together. So we're going to multiply the numerator, multiply the denominators, and we'll get x to the 2/10, but we're going to reduce it to x to the 1/5. There's nothing hard about number 15. We've got one base, okay, raised to a power, and then that whole thing raised to a power again. So again, it looks like number 6 at the top. So we're going to rewrite the base, multiply those fractions together, multiply the numerators, multiply the denominator, and I get 2/14, but I need to reduce that to 1/7 for my final answer. All right, 16. 16 is a fraction raised to a fractional exponent. So just follow the rules and everything will work out. We're just going to start with that numerator, which is x squared, and we're going to raise that to the 1/3 power. All right, so I'm going to write it in like this for now. We'll go back and simplify it. And then that 27 is also raised to the 1/3 power. We're following the rule for how to raise a fraction to an exponent. That x squared to the 1/3 power is a power raised to a power. We only have one base of x, and then we've got the squared being raised to the 1/3, so we're going to multiply those two together to give us an x raised to the 2/3 power. And then down here we have 27 raised to the 1/3 power. So in order to evaluate that, since that's a whole number there, it's not a variable, I can put it into radical notation, which would be the cubed root of 27. All right, so my numerator is good. It's simplified, but I can take the cubed root of 27 and I can simplify that down. Since that's a perfect cube, 27, 3 times 3 times 3, then I would pull a 3 out from under the radical, and this would be your most simplified answer. All right, we have a radical in number 17. We have a cube root, and the radicand is 16, x to the 4th, so a variable with a coefficient. The variable is raised to an exponent, but again, we're following the same rules. I'm going to put it in parentheses, and the cubed root of 3 is the same thing as the 1/3 power. So I'm raising that whole thing to the 1/3 power. But actually, now that I'm looking at it, I think the easier way to do it is to just prime factor what's under here. And I'll show you how to prime factor that x to the 4th. So we have 16, and if that is prime factored, we end up with 3 2's and 1 2 left over. All right, so we know we're going to be able to pull a 2 out. I'm going to leave a little space here for our x. I'm going to rewrite the cube because I've got to leave the 2 from over here in the prime factor tree that's left. I've got to leave that under the radical. Now I need to deal with the x to the 4th. Well, you know x to the 4th is 4 x's multiplied together in a row. So I can take 3 of those out, just like I took 3 of the 2's out, and I can take 1 of those x's out, or 3 of those out and label it as an x. So it would be, this is probably not super necessary, but if I were prime factoring it, it would look like, that's supposed to be a 2, this, that, and that. Okay, so that would be the prime factor tree for the x to the 4th. But I don't really need to do that. You know that there are 4 x's multiplied together to give you x to the 4th. But what I want to show you is, look, I can pull 3 of them out. I can write it out here like I did next to the 2, and I have 1 x left over here that has to be left under the radical symbol. So there would be your final answer. So you can prime factor variables out from under the radical symbol as well. You don't have to write out a prime factor tree. I just was trying to illustrate to you that it's the same idea as the 16. All right, number 19, we have 2 exponential expressions. The bases are the same. We're dividing them, so we're going to rewrite the base, subtract the fractions, or subtract the exponents. 7/5 minus 4/5 gives us 3/5, and that one was nice and easy for us. Number 20, we're going to do the same thing we did on number 17. We're going to prime factor 64, and then we'll pull out our x's and any y's that we can, if that's possible. And then we will, we also need to take care of the denominator. So let's start with that numerator. We're looking for the cubed root of 64, which fortunately for us, the 64 is a perfect cube. So 4 times 4 times 4 is 64. So we can pull that out from under the radical. X cubed is also a perfect cube. That's x times x times x. So we can pull the x out. The y, we only have one single y by itself, so we have to leave that under the radical. All right, now the denominator. We know that we cannot leave that x to the negative third in the denominator. That's not simplified. We're not allowed to have negative exponents in a simplification. So we've got to pull that up to the top here. So I rewrote the 4. The 4 is fine. I'm going to pull that up here and multiply it. I'm going to have to remember that this is all being multiplied in the end, that x cubed. All right. And then here I'll leave the y down here because the y is fine. So let's take care of that x cubed. Now look, these are not, I'm not foiling here. I'm just going to multiply like terms. That numerator, if I were to stretch it out and show you what's happening here, it's really 4 times x, no, not x cubed, times x times the cubed root of y times now this x cubed. All right, so I'm going to, remember, if I'm multiplying together exponential expressions, I'm looking for things that have the same base. So the only things that have the same base are these two right here. So I'm going to call it, instead of x to the first times x to the third, it'll be x to the fourth. So that new numerator up here is 4x to the fourth cubed root of y. And then down here I have a 4y. There's one more simplification we can make, and that is to divide the 4's with each other. And so we end up then with x to the fourth times the cubed root of y over y. We can't cancel the y's because technically this is y to the 1/3 and this is y to the first. So we're going to just leave it like this. This is simplified as far as we can get it. All right, now moving to the back of the sheet, I want you to take a minute to notice the difference in operation between the front and the back here. In the front, we were either multiplying two expressions together, or we were dividing two expressions together, or we were just simply simplifying an expression. On the back, we are adding and subtracting exponential expressions and or radical notation. All right, so it's important that you notice the difference because we're going to be following different rules. So like on 25, so if you don't see that right away, just pause the video, take a minute, study the front, and see how it's all multiplication and division, or raising a power to a power, or just simply putting together the rules for simplification. And then here on the back, we're adding and subtracting. And then start the video back up. On number 25, the way that literally reads is that we have 6 cubed roots of 5 plus another 2 cubed roots of 5. It's almost like if you replace the cube root of 5 with the variable x, then it would say 6x plus 2x. And you would know that would be 8x. It's the same idea. Okay, so we have 6 cubed roots of 5. We're adding 2 to that. And so we end up with 8 cubed roots of 5. That's the final answer. On 26, now on this one, the radicals don't match. The radicand, what's underneath of it, doesn't match. So we have to do some simplification on the square root of 45 to see if we can make it look like the square root of 5. Okay, so right now they're saying 5 square roots of 5, take away the square root of 45. But if we go ahead and prime factor 45, because that's what we would have to do anyway to get that 45 out from under the radical. I mean, we would have to do this anyway. We can see that we have 2 3's that can be pulled out from under the radical and 1 5 left over that's going to be left under. So then if we rewrite this, we end up with 3 times the square root of 5. So 3 square roots of 5. All right, and they asked us to subtract 5 square roots of 5 from that. So we have 5 square roots of 5. We're going to take 3 square roots of 5 away to leave us with 2 square roots of 5. On 28, what's under the radical is the same. We have the square root of x and another square root of x. We have 2 square roots of x here, and we're going to add to that 7 square roots of x. So 2 square roots of x plus 7 square roots of x give us 9 square roots of x. Now on number 29, we have to do some simplification before we can do any combining. So maybe that's a good way to think about it, is that if the like in 25, 26, and 28, we had to double check and see if what was under the radical, if they matched. So in 25 they did, so we didn't have to do any simplification. And 26 they didn't. The 5 and the 45 didn't match, so we had to simplify the square root of 45 until they did match. 28 they matched, so we could just go ahead and combine them. So before you combine, whether it's adding or subtracting, make sure that what's under the radical matches. Same thing down here in 29. We have to simplify before we can combine. So we have this kind of term, this term over here, and we're going to combine it through subtraction with this. But we've got to simplify because they don't match right now. They're not simplified enough to combine. So we're going to follow our rules for exponents. I have 3. I'm just going to leave that as is. I have this whole thing in parentheses being raised to a power. So x to the 1/2 raised to the 2nd power. I'm multiplying. X to the 1/2, if I were going to write it out, it'd be x to the 1/2 squared, and then it would be y cubed squared. All right, so x to the 1/2 squared is just x to the 1st. It's x to the 2 over 2, which is just 1. Y to the 3rd raised to the 2nd is y to the 6th. All right, we'll do the same thing on the second term. X cubed raised to the 1/3 power is x to the 1st again. It's x to the 3 over 3, which simplified is x to the 1st. Y to the 18th times 1/3 is 18 over 3, which is 6. So y to the 6th power. Right, if you're not quite following me, I'll write that out over here. It's x to the 3rd raised to the 3rd, right, times y to the 18th raised to the 1/3. So we're just multiplying those exponents together when we do that. Now we have like exponential exponents. We've got x y to the 6th. We have 3 of them. 3xy to the 6th minus xy to the 6th. So we're just going to combine what we know, and we'll end up with 2xy to the 6th. All right, and then last here, we need to write these expressions in this most simple form we can get them. And so there's no new rules here. It's just a little bit more challenging because we're going to have to think about these variables here and how to kind of prime how many roots are coming out. So let me just start 31. We're looking for fourth roots, and so we know for 3 there is not a fourth root of 3. We don't 3 is prime, so we don't have to do anything with that. So I'm going to end up leaving that under the radical. But this x to the 7th, if I come out here, if x to the 7th is really 7 x's, okay, so that's if I'm looking for pairs of 4, what I can say is I will have 4 x's that could come out, and then I have to remember that I'm going to have 3 of those, 3 left over. Okay, so I can pull 4 x's out, and I'm going to put the x right there to notate that I took 4 of them out, but I've got to remember to leave 3 of them under there. Same thing with the y, although with y to the 9th, all right, remember again, we're looking for pairs in 4s. Well, I can take out 4, and then I can actually take out another 4 of them, and then I'll just be left with that 1. So I can take out 2 y's, so I would label that as y squared. Don't write y times y or yy. We want to just, simplify it, y squared. I'm going to end up having 1, though, that has to be left under here. And then z cubed, that's 3 z's. There aren't a group of 4 of them, so we can't pull any z's out. So we have to leave that under the radical like that. Okay, and then, technically we really should have the x first, and then the y, in ABC order. Okay. So in 32, think about what we're doing here. We are multiplying radicals together. So the rule states that in order to multiply radicals together, we can put them all under the same radical symbol and multiply the things that are alike. So x cubed times x would give me x to the 4th. Remember, when you're multiplying together exponential expressions, you're adding those exponents. Then if we do the y's, we'll end up with y to the 5th, and we would end up with z to the 5th. Now, again, we have to go back up here and see that they asked us to simplify this as far as we were able. And so we can take the square root of some of these things. X to the 4th, that's 4 x's, so that's 2 pairs of x. So that means we can pull out 2 of them. Okay, an x and an x, which would leave us with x squared. Y to the 5th, all right, let me write this one out. So y to the 5th is a product of y squared times a y. So again, I can pull out 2 y's to give me y times y, which is y squared, but I've got to remember to leave that one y that won't come out. It doesn't have a match, has to stay under. And then z to the 5th, we can see that we need to do the same thing. I should have left some space here, but it's the same deal as the y to the 5th. We can take 2 z's out, and then we're going to have 1 z left under the radical. So the final answer there is x squared, y squared, z squared times the square root of yz.